Hello everyone, this is Skylar. Today I'm going to talk about two different factors in my sport, which was deadlifting, or powerlifting, but deadlifting specifically. The first thing I'm going to talk about is Newton's laws, and then after that I'll talk a little bit about energy. So the first thing I'm going to do is show you the clip. Probably have seen a similar clip before from earlier in the school year. So for Newton's first law, it states that an object stays at rest unless an outside force acts upon it. So basically, this bar is not going to raise itself. I had to lift it. So that's obvious, but let's discuss how much energy is actually needed to get the bar off the floor. So that's going to take us to Newton's second law, where it states the sum of the forces on an object multiplied by its acceleration will get lost my place. In order to get the weight to accelerate from its rest to your lockout, aka, I'll show you here, the lockout is the top of the movement, basically where I stop lifting, right there. So in order to get it to your lockout, the net force has to be positive, which means you have to apply more force to the bar than the gravity pulling it down. So moving on to Newton's third law, it's kind of known as the action-reaction law, and this describes the forces between two bodies. And in this case, the two bodies the first one is me and the weight of the bar itself, and the second body is the earth. So we exert a force upon the earth with our feet, so right here, and the earth will push back with an equal force. And I know that's true because when I lift this bar and putting all that force to my feet, I don't just fall through the floor. So we know that's true. Unlike a squat, there's potential energy when you start a squat. So when you pull the bar off the rack and you're getting ready to go down into the squat position, you have all that potential energy that's as the weight travels towards the ground. But with a deadlift, there is no potential energy. It's a dead weight. So starting from the ground, there's no potential energy. And the way that the potential energy or energy needed to lift the 75 kilograms as shown is found in the equation times mass. So I worked it out and I found that energy equals 75 kilograms, that's the weight, times 9.81 meters per second squared, which is gravity, times 76.2 centimeters, which is the distance it travels from the ground to lockout. When I worked that out, I got 56,064 joules. So that's the energy I needed to lift the weight. That's the starting energy to lift the weight from the ground. So that's not a consistent amount of energy through the whole lift, but it is the most energy you'll need to lift the bar during this movement. The most energy you need will be in the beginning of the movement. So the hardest part is just getting the bar off the ground. After that, you'll have a little bit less energy. And then another thing to consider is that the bar must travel as close to the person's center of mass to minimize unwanted horizontal energy. So the goal here is basically to stay as vertical as possible. I'm keeping it close to my shins to make sure that there's not any other outside forces acting upon it. So that being said, we do know, because we study this, that there are outside forces like friction and thermal energy, stuff like that, but we're not considering that in this example. I hope that this example is able to explain a little bit better how Newton's laws and energy play a factor in the deadlift. Thank you.